Hello, welcome to part 3 of Chemistry Paper 2. Let's start. We finished there at the end of ceramics. Let's go on to the next one. So, polypropene is an example of a polymer. The structure of polypropene molecule is shown in figure 5. Okay, this polymer is made from a monomer. So that's the monomer there. Draw the structure of a monomer molecule showing all covalent bonds. Okay, so let's have a look. So it's made from a monomer. So we've got polypropylene. So it's got C. Okay. It's got a CH3 group. That's what I'm drawing now. Okay. H. Be careful the bonds here. H. Okay, so yeah, it has to have a double bond though. It's a monomer because it can open up to form a polymer. So when it's a monomer, it's got that double bond. Okay, so that's the thing. It's the same thing as that really, but it's got a double bond. Also, make sure you put all the hydrogens in too. Okay, a layer of polychloroethene, PVC for short, is used to surround the copper in electrical cables. Explain why polychloroethene, PVC, is a suitable material for this process. Okay, so number one, it's an insulator, isn't it? So PVC, we have to write the whole thing out again, is an insulator. So it's an electrical insulator. Also thermal as well, but in this case, electrical is more important. Okay, and also it's a safety thing too, isn't it? Also prevents electric shock. Okay, it could be. There's a lot of things you could have written there that will still get you marks. Okay, so they would allow flexible, less likely to break than materials is true. Inert, unreactive. Yeah, I wouldn't write that, but they give you a mark still because it's not really to do with this question, but they'll give you a mark. Yeah, waterproof would be another one. I was going to say that's also useful. So, but I've written 2 there. There's a few that I've just said that you could also have written. Now, some polymers are polyesters. Okay, we know that's material, don't you? What type of reaction takes place when polyesters are formed? Okay, so I always remember this one. When you make a polyester, you actually mix 2 materials together, and you dip a stick in it, and you pull it out, and the polyester is attached to it. Okay, so it's actually a condensation reaction because it occurs on the surface. Okay, and it occurs on the surface. So if you look up about how polyesters are formed, watch a video. Okay, it's a good thing to watch that because it's a condensation reaction. Have a look. The repeating unit in a polyester molecule is shown in figure 6. The polymer is made of 2 different monomers. Draw a molecule of each monomer showing all covalent bonds. Okay, so there's 2 going on. Let's start with the top one. Okay, so we've got 3 C's together. It's a bit tricky, isn't it? 3 C's. We've got that double bonded oxygen. We've got the 2 hydrogens. Remember, carbon can only form 4 bonds. H. We've got another, okay, O. H. And then with this one, we've got 2 C's together. O. H. O. And when you've got a line like that, that means it's bonded to something else. So it'll be H's. If it's just a line with nothing on it, that means it's a H. Okay, so is it's quite a tricky one to do because it's got a line. That means there's a H there with that one. Okay. Give the name or formula of the small molecule formed when the monomer reacts to form an ester link. Okay, so actually, if you think about it, okay, what's going to be lost when the monomers form? You actually get water. So when the monomers react, it's H2O. You actually get water being formed. Right, number 6. So crude oil is a complex mixture of substances. Crude oil can be separated into useful fractions by fractional distillation. Figure 7 shows a fractional distillation column, this one, and the fractions produced when a sample of crude oil is distilled. So you've got bitumen at the bottom, fuel oil, diesel oil, kerosene, petrol, and gases right at the top. The properties of these fractions vary from the top of the column to the bottom of the column. Which of the following is a trend in a property of the fractions obtained from the top of the column to those obtained at the bottom? Let's have a look. So the average number of carbon decreases. No, it increases. That's wrong. The ease of ignition increases. No, bitumen's like tar, so it's not easy to ignite that. The boiling points decrease. No, they increase. The viscosities increase down. That's the only one that's right. The viscosities, because yeah, the bitumen's like tar. Okay. Most of the substances in crude oil are alkanes. Which of the following is the general formula of an alkane? Okay, general formula of an alkane. So if you think about it, if you forget, alkanes have got a single bond. Right, so let's have a think. So we've got the first alkane is methane. Okay, the next one, ethane. Right, so let's write the, right, that's CH4, that's methane. Then C2, 1, 2, 3, 4, 5, 6. H6. So what's happening is that if that's doubling, so CN, 2N, we did that one. So 2N, and we did plus 2. So CN, 2N, plus 2. We weren't sure, we could even do another one. We could do propane. Okay, so let's put it up here. C, H, H is propane. H, and the H is H. So that's C3, 1, 2, 3, 4, H8. Okay, so that's BCN plus 2 again. So to make sure we test it. Okay, explain why alkanes are described as hydrocarbons. Okay, so this is nice and easy because they contain hydrogen and carbon only. So they only contain, this is important, but only. Lots of molecules contain hydrogen and carbon, but not only hydrogen and carbon. Train. They contain only hydrogen and carbon. Cool. Next one. Figure 8 shows a graph of the boiling points of some alkanes against the number of carbon atoms in one molecule of each alkane. So we've got boiling points, number of carbon atoms in one molecule. So the more carbon atoms, the higher the boiling point. Okay, so that's the question. So it's kind of said it. Right, so yeah, so or the boiling point, and it says explain as well. Okay, so a little bit extra. So the boiling point increases as the number of carbons increase? Because the forces between the molecules increases. Cool. That's it for 2 marks. Nice and easy, really. Just a second bit you have to remember. So, D, when crude oil was separated into fractions, the amount of each fraction obtained rarely matches the demand for that fraction. So it means that sometimes, obviously, the demand means obviously how much is wanted in the world. For example, getting petrol, yeah, it's got very high demand, okay, but obviously the fraction we get doesn't meet the demand. Okay, so it says figure 9 shows the relative amounts of 6 of the fractions present in a crude oil, and the relative demand for each of these fractions. Relative amount, so you've got relative amount fraction, so the dark one's the relative, but the pale colour, the white one, is the relative demand for the fraction. For fuel oil, we get a lot of fuel oil, but there isn't actually much of demand. And I said about the petrol, I knew about that one, the relative demand for petrol is actually higher than what we get. So cracking, we can do something about that. Cracking is used to match the relative amount of a fraction of crude oil to the demand for that fraction. Use the information in figure 9 to give the amount of fraction that is most likely to be cracked. So cracked means it goes from a big molecule to a small one. So fuel oil, okay, we've got so much of it. It's fuel oil. So that can be actually cracked down into petrol. Okay. So in a cracking reaction, reactants are heated to form products. This reaction is endothermic, so it takes in heat. Okay, on the axes provided, draw the reaction profile of this reaction. Label the energy of the reactants, the energy of the products, and the activation energy of the reaction. Okay, so it's endothermic, so the reactants start down here, we'll put it down the axes. We need the reactants. Okay. Heat energy. Then we have products. The activation energy. Okay, so yeah, the products is endothermic and going to be higher than reactants. Okay, in that case. So yeah, the main thing there was remembering it was an endothermic reaction. So yeah, the products are going to be at higher energy than the reactants there. So next one. So dodecane C12H26 can be cracked to form useful products. Complete the equation for the cracking of dodecane. Okay, dodecane by filling in the formula of the single molecule needed to balance the equation. There's only one molecule there. So all we've got to do is look at and count them up, isn't it? So got six carbons there. There's 12 over there. So whatever it is, it's going to be C6. Okay. And then we've only got hydrogen and carbon. So H. So 3. So be careful of that. So 3 times 4 is 12, and it's 26 there. So it's going to be H14s. Just the left-hand side has got to equal the right-hand side. That's all you need for that. Okay, so 7. Describe what is seen. So we see when chlorine water is added to potassium bromide solution and the mixture shaken. Okay, so it says when chlorine water is added to potassium bromide solution. So potassium bromide solution. So what I'm actually going to do, it's going to take a while to answer that question. what I'm going to do is I'm going to carry on answers to question 7 in part 4. Okay, so thank you for listening, and I'll continue into part 4.